All right, chapter 6, we're going to be talking about exponentials and logarithms. And 6.1 is about exponential functions. And so what we're going to do here is just sort of give an introduction to exponential growth and look at a couple of applications. And we'll wait until 6.2 to look at the graphs of exponential functions. So first up, let's look at exponential growth. Exponential growth occurs when you have a situation where the rate at which a quantity grows is proportional to the size of the quantity. Another way of saying this is that the quantity is increasing by some percentage. And I've got an example here. A city's population is 100,000 in the year 2000, and then every year the population grows by 1%. Now, the thing that makes this like compound growth or exponential growth is the fact that 1% of the population, as the population gets bigger, 1% of it's going to get bigger as well. So it's not going to be growing at a linear rate where every year it adds on a certain amount. Every year it's going to add on 1% of it. So if you look at this, year 2000, the population is 100,000. So in 2001, what we have is the original 100,000 people plus another 1%. So we've got 101,000 people. And then in 2002, we've got the 101,000 we start with. Then we add on another 1% of them. Now we've got 102,010 people. So notice the first year we grew by 1,000, then by 1,010. And then the next year by a few more. It looks like 1,020.1. I guess I should have rounded to the nearest person, but anyway. So the easy way to work this out, though, is to look at this. When you do this 100,000 plus 100,000 times 1%, that's 100,000 times 1 plus 0.01, or 100,000 times 1.01. So every time we raise the population by 1%, we're multiplying by 1.01. So to go from 2000 to 2001, we took that original 100,000 and multiplied it by 1.01. And then we do the same thing again. From here to here, we multiply by 1.01. And so that's the same as taking the original 100,000 and multiplying it by 1.01 twice. And you can see that here. If you take just 1.01 and start raising it to powers, if I square it, notice that's what we got for the population, that times 100,000. If you take 1.01 and cube it, it gives you this. And so if you wanted to know what's the population going to be at a certain time, say after n years, it's going to be 100,000 times 1.01 to the n. So just for instance, if we wanted to know what the population here was going to be in 2020, that's going to be 100,000 times 1.01 to the 20th. And when I put that in my calculator, I've got it written in my calculator looking like this. When I hit enter, it gives me this for my population, which looks like that would round off to 122,019 people. All right. So this is an application with population. Let's look at compound interest. This is a really useful application of this. Compound interest is something that grows exponentially, and the equation that we use for it is this. You got a equals p times 1 plus r over n raised to the nt. Now let's look at where all this stuff comes from. A is the accumulated amount, which is like the amount of money in your account. P is the principal, which is the amount you put in originally. R is the annual interest rate as a decimal. N is the number of compounding periods per year, and T is the time in years. So this is going to need a little bit of explanation about how you deal with the number of compounding periods. Let's do this example. Suppose you invest $500 in an account that pays 2% interest compounded quarterly. Okay, so what it means when they say compounded quarterly, it means instead of giving you 2% all at once, at the end of each quarter, they give you 1/4 of this. So at the end of each quarter, your account is increased by, in this case, 2% divided by 4, which is 0.02 over 4, which is 0.005. So in other words, increasing by that amount is the same as multiplying by your balance is multiplied by 1.005. And that happens 4 times in that year. So if we wanted to work this out, we're looking at, what we say, 5 years. So 5 years is 5 times 4 is 20 quarters. So the amount of money you'll have at the end of that is going to be 500 times 1.005 raised to the 20th. And there's no good way to do that other than just on the calculator. Now, when I do that, I get, okay, that's not right. Oh, I put in 5,000 instead of 500. Let me delete a 0. All right, so the amount of money you'd have here is $552. And round to the nearest penny, 45 cents. I'm not sure if you can see that. But on this one, we kind of did everything manually, going in and finding the 1.005 and all that. Notice this 20 up here is, well, let's go back and label these things. In this problem, my A was 500, or my A is what I'm looking for. My P is 500. R is 0.02, and N was 4, and T was 5. But we took all that stuff into account. This right here is 1 plus R over N. This up here is N times T. So let's do another example or two and do it by using the formula directly. So suppose you invest $7,000 in an account that pays 3.6% interest compounded monthly. How much will be in there after 5 years? All right. So accumulated amount we're trying to find. Principal is what we put in, 7,000. The rate is 3.6%, which is 0.036. All right, N in this case, since it's compounded monthly, that's 12 times per year. And the time we're looking at is 5 years. So we can take all this and just plug it straight in. The amount we want that we'll get is 7,000 times 1 plus r 12 raised to the 12 times 5. All right, now I'm going to put that into my calculator. 7,000 times 1 plus 0.036 over 12 raised to the 12 times 5. Now, depending on the calculator you have, you might put this in differently. When I do this, I get 88, or no, I get 83.78.26. Looks like I've got a decimal in there, but I don't. 8378.26. I do have a decimal, but it's before the 26. Now, when you put this in your calculator, depending on the calculator you have, you need to be careful of a couple of things. Mainly this one down here, this 12 times 5. On the calculator, unless you have a calculator that actually puts that up as an exponent, like, up high, you probably need to put parentheses around it. Otherwise, it'll do this, raise it to the 12th power, and then multiply by 5. So order of operations is important. Let's see. I thought I had a TI calculator, but I've moved it somewhere else. But on my Casio here, this is what I put in to get this. Got 7,000 times 1 plus 0.036 over 12, then raised to the 12 times 5. Of course, you could also just multiply it out and get the 60, and 36 over 12 would be 0.03, so 0.003. So anyway, just make sure you get the order of operations correct. Okay, let's look at this one. Suppose you invest $500 in an account that pays 2% interest compounded quarterly. How much will be in the account after 5 years? Is that the exact same thing we did earlier? That is. Let's change this problem to make it more interesting. Let's say it's 3% interest compounded semi-annually. All right, so for this one, A, P, R, N, T. A is what we're looking for. P is 500. Our rate is 3%, which is 0.03. Okay, semi-annually is twice a year, and T is 5. So I'm going to do A equals 500 times 1 plus 0.03 over 2 raised to the 5 times 2. I'm going to do this one by hand, at least the multiplication part. So let's see, that's 0.03. You divide that by 2. I got to be careful. I got a mistake here. 0.03, you divide that by 2, you get 0.015. And this is raised to the 10th. So let's see. 500 times 1.015 raised to the 10th is $580.27. I feel I would be remiss if I didn't mention one thing. Interest rates right now are terrible. I think it would be pretty much impossible to find an account that pays 3% interest right now on a balance of $500. If you were a super rich person, you might be able to find one that would pay that on a big account, like with hundreds of thousands of dollars in it. But 3% is not really a realistic interest rate right now. All right, this video is long. I'm going to stop it here, and I'll pick up with solving for r in the next one.